So let me thank the organizers of this event, of the festival, and in particular the local people here. I didn't expect to visit Bilbao, but it's a great pleasure to be here today with you, and also to have an opportunity for looking at the beautiful museum, Guggenheim Museum. It's really great. Let me start with the first slide, if I may. Maybe we have to switch from one line to another. That's it. So I'm going to talk about molecular machines, and especially we will explore the world of biology very briefly, and we will move towards chemistry in the second part of my lecture, which will be the main part. I know for sure that most of you are not great chemists, or maybe I'm wrong, but you know your knowledge of chemistry is what it is. And I thought that maybe we can perhaps talk about simple things at the beginning, to remind you what a molecule is. A molecule is a set of atoms, and these atoms are connected with one another by chemical bonds. And here you have a very simple molecule, which is benzene. Benzene, it's a toxic molecule, not terribly toxic, but it's a toxic molecule. But nevertheless, it's important to know its chemical structure. And so this is, let's say, the old way of representing benzene. It's a hexagon. This is the most modern way. We do not indicate that there are carbon atoms here at the vertices, the 6 vertices of this hexagon. So this is benzene. So we have the choice between 3 representations. Another very simple molecule is cholesterol. Well, maybe it doesn't look so simple to you. Cholesterol is important, as you know, well, especially the more you get old, the more it is important. And again, here, the carbon atoms are just represented by those vertices. We do not write C or CH. And so this is a relatively simple molecule, as I said, but much more complex than benzene. Now a molecule which I would like to discuss with you, because it's really a fantastic molecule, which was discovered completely by accident. In English, we say serendipity, which means a happy accident. And the people who discovered it were trying to look for molecules found in space, in the interstellar space. And so they did some nice experiments, but they couldn't find the molecule they were looking for. But instead, they made this molecule. It's a soccer ball. It's a nano soccer ball, C60. You have 60 carbon atoms arranged exactly as the 60 vertices of a soccer ball. And the reason why I like to talk about this molecule is because of its size. It is 1 nanometer large, or let's say the diameter of this compound is 1 nanometer. And 1 nanometer, probably everybody knows that 1 nanometer is small. But how small is it? And I just take a very simple image. The ratio between 1 nanometer and 1 meter, well, let's assume that 1 meter is here, is roughly the same as the ratio between a small bar, which is 30 centimeters long, and the distance between the Earth and the Moon. And that probably speaks to all of us. So the nanometer is small. Now let's look at molecules from a more general viewpoint. Most molecules are considered as still objects, static objects, even if they undergo stochastic deformation, distortion. But these molecules, the millions of molecules that have been made by chemists, were considered as motionless. Now let's look at biology. In biology, the situation is dramatically different. In biology, controlled molecular motion is absolutely essential. It governs lots of very important functions, very important reactions. We find, just a few examples, rotary motors, linear motors, even walkers, molecules which walk on the road, systems which contract or expand, elongate at will. And these species are called motor proteins. So motor proteins, this is a very important family of biological molecules which are absolutely essential to life and omnipresent. You cannot think of any important biological process not involving motor proteins. Two, let's say, reasonably simple examples. The first one is probably the most important. ATP synthase. This is the enzyme which is responsible for the synthesis of ATP. ATP, maybe some of you heard of that, some others didn't. This is adenosine triphosphate. This is the fuel of life. Each time you need fuel, you will consume ATP. And each time you can rebuild your energy, you will convert the degradation product of ATP to ATP, back to ATP. And it's a rotary motor. The enzyme which is responsible for that is a rotary motor. It's an enzyme which is present in all living organisms, even the most primitive ones, the archaeas, which appeared on Earth about 3.8 billion years. They function with ATP synthase. And don't take it bad, but archaeas have probably about the same ATP synthase as yours. So in evolution, nothing has really changed as far as energy, biological energy, is concerned. And so there is a beautiful video on the internet, which I downloaded. So this is ATP synthase, which is partly embedded in a membrane in the cell, not in bacteria, but in the cell, in mitochondria, to be more specific. And it works as a rotary motor. So here is the membrane, and you have a proton gradient, which is consumed. So protons are transported from one side of the membrane to the other side of the membrane. And this forces this big cylinder to spin. And as it spins, there is some kind of shaft or axis, which is threaded inside the cavity of this cluster of proteins, which spins as well. And this is the spinning motion which is responsible for the making of ATP, which is a purple species, from ADP and inorganic phosphate, the two simpler molecules. One sees them arriving here, ADP and inorganic phosphate, and ATP is made. It's not very fast on the video, but in fact it is much, much faster. It spins at about 80 rounds per second or so, like, let's say, a normal engine, a car's engine. Another example, which is perhaps even more spectacular, and it's a video which was made by biologists in Harvard. This is the kinesin. So we can easily imagine that in the cell, there are factories making molecules at some places in the cell, making even very complex molecules. And these molecules have to be dispatched. They have to be carried from one spot to another point. And this is done by a transportation system, which is very, very efficient. So in the cell, there are rails or highways, if you prefer. And these highways provide the means for this little thing here, which is the kinesin, to travel, to walk. And if you look carefully, you'll see it's a walker. And at the back of this kinesin, there is a huge bag. And this is an organelle. This is a set of molecules which have to be carried from one spot to another point within the cell. And if you look, it walks. It's really a walker. And this is not science fiction. This is based on very detailed scientific studies. Each step is about 8 nanometers long, and it can walk very, very fast. It can do 100 steps per second, which means that if you consider that this is a human being, let's say this is the size of a human being, at its maximum speed, it would run at about 800 kilometers an hour. So that's very impressive compared to human beings. So now the question is very simple. In biology, there are plenty of beautiful molecular machines. We chemists, synthetic chemists, are we able to make similar species, or at least species which can be set in motion in a very controlled fashion? So can we synthesize things which are reminiscent of motor protein? And of course, the question has a very simple answer. Yes, to some extent, yes. Now we will switch completely towards hardcore chemistry and talk about 2 families of molecules which were basically unknown before the mid-80s. So this is a catenane. It's a very simple species. You have 2 interlocking rings. Catenanes, the word comes from Latin, catena, which means chain. It's probably very similar in Spanish. In Italian, it's also catena. And in Spanish, is it cadena? Or, yeah. So it's a very small chain, 2 cyclic links. And here you have a rataxane, very similar to that, an axis which is threaded through a small ring and 2 bulky groups to prevent the system from dissociating. Why are these molecules exciting in relation to the field of molecular machines? Very simple. If you have a simple rataxane like this one, if you are able to set the system in motion so as to move the red ring, which was here originally on the left part of the axis, to the right part, and perhaps go back to the original state, you are very close to making a linear motor, exactly like a piston moving in a cylinder. If you can rotate the ring here about the axis on which it has been threaded, you are on your way towards rotary motors. And similarly here, if you can spin this ring, you are close to making a rotary motor. And so the people became very excited about this idea of using catenanes and rataxane for making molecular machines. But there was a problem. These molecules were basically unknown. And so we had to find some trick for making catenanes and rataxane. And in our group, when we started in this field, before doing this work, before trying to make catenanes and rataxanes, we had a big project which was related to the photochemical cleavage of water to H2 and O2. So this is a dream reaction, of course, because if you can use solar light plus water to make hydrogen, it would be a big step towards non-polluting fuels. And there were, and there still are, many, many research groups in the world trying to split the water molecule to H2 and O2. So we were interested in that. and using a molecular approach. And the molecular approach we used was based on molecules, highly colored molecules, able to harvest solar light. And those molecules were containing a copper atom. So this is what the people call a complex. Chemists call that a complex. It's not that complex, but it mixes a metal or an ion, an organic fragment. This is an organic fragment. And so this molecule was quite interesting in relation to water splitting, but it had another property. And we did this work mostly in collaboration with a good friend, Dave McMillan in the US at Purdue University in Indiana. And if you make the molecule here, and if you look at it carefully, you realize that you have a nice trick for making catenanes. If you are able to connect this point to this other point, you will make a ring which will be embedded in a vertical plane. And in an analogous way, if you are able to interlink this point and that point, you make a ring, another ring, lying in a horizontal plane. And these two rings are interlocking. And so we thought, so we have some nice trick to make catenanes. And it was a difficult decision. Shall we continue to do work related to water photochemical splitting, or should we jump in a completely unknown field? And we jumped in the completely unknown field. And after 1 year, we had our first paper, thanks to the talent of a great synthetic chemist who was working with me, Christian Dietrich Buschecker. And we published in French. That was kind of a provocation, publishing in French at the time was somewhat unusual. And we published in a journal which was not a super good journal, but let's say a reasonably good journal. So let me show you some videos. If you see the videos, you will immediately understand how it works. We start from this molecule, whose real chemical structure is indicated here. And now we will mix with copper. We obtain what we call the entwined molecule, the entwined precursor. And from that, you make a ring on the right, another ring on the left, and you have your catenane. Very, very simple. 2 steps or 3 steps, and you can make 1 gram of a catenane. Another strategy was a little bit more complex, but not exceedingly complex. You can make a ring of this type with 2 nitrogen atoms in blue here. And these nitrogen atoms will be happy to interact with copper. So what you will do, you mix with copper, you add another organic fragment, and finally you make the second ring. So let me do it again because it's a little bit too fast. Copper, another organic fragment which threads in, and finally you make your ring. And this now would be a 3 to 4 chemical step synthesis, so very, very simple. Now let me show you the first molecular machine we made in Strasbourg. That was already a long time ago. It was what we call a swinging catenane or an oscillating catenane. And we will do a little bit of coordination chemistry, inorganic chemistry. Nothing terribly sophisticated. You know that metals lead to ions. Iron, let's say when you oxidize iron, when you corrode iron, you obtain ions, iron 2+ or iron 3+. And the same is true for copper. If you have a bar of copper metal, when you corrode it, you will obtain ions, either copper 1+ or copper 2+. And there is something very special with copper. Copper 1 plus likes to be surrounded by 4 nitrogen atoms, not more than 4. Copper 2 plus is more demanding, and it prefers to be surrounded by 5 nitrogen atoms. And we will play with that. So we start from this molecule. Again, not very complicated. It's a catenane. We can make it reasonably easily. And at the back of the molecule, we have introduced a fragment which contains 3 nitrogen atoms. So this molecule now is very stable because it is copper 1 plus, in red, copper 1 plus, and you can count, you will find 1, 2, 3, 4 nitrogen atoms. So the copper 1 plus ion here is smiley, very happy. Now you will make it less happy. You abstract an electron from copper 1 plus, and if you abstract an electron from a 1 plus species, you generate a 2 plus species, naturally. So you go from here to here with now a 2 plus copper ion, and copper 2 plus prefers to be surrounded by 5 nitrogen atoms. So very simple. The molecules have everything it needs to satisfy copper 2. The fragment, which was here originally with 3 nitrogen atoms, will move, kick out this fragment, which only contains 2 nitrogen atoms. And at the end of the motion, you will generate a copper 2 plus species, which is very stable because it contains 5 nitrogen atoms. And the copper 2 ion is surrounded by 5 nitrogen atoms, a very happy copper 2 ion. You can go back, you reduce, so you inject an electron in the system, you generate a very unstable species because copper 1 plus hates to be surrounded by 5 nitrogen atoms, and you will rearrange and regenerate the starting form of the molecule. It's not that complicated, is it? Now, there is a nice video, I hope. I mean, I didn't make it myself, but a student of mine, which will perhaps explain you the principle. So we start from the same molecule. We have either copper 1 plus or copper 2 plus. And the 3 nitrogen atoms we had seen on the previous slide are now represented here. 1, 2, 3, 4 nitrogen atoms around copper 1, a very stable species. Now we abstract an electron, we generate copper 2 plus. The system has to rearrange in order to satisfy copper 2. And we have a 5 coordinate or 5 nitrogen atoms around copper 2. You can go back, you inject an electron again, abstract an electron again, and you can do that as many times as you like with the computer, but also with the molecules. This is the beauty of the system. We have never detected any fatigue, any degradation. At the same time, more or less, our good friend Fraser Stoddart and his group published a very exciting system which they called a molecular shuttle. A molecular shuttle, meaning that there is some kind of bus going from the airport to the to the city center, or from the grain station to the rail station, and that works beautifully. It's quantitative. You send a signal to the molecule, which is again based on electron transfer, and the system works perfectly well, very, very clean. So everybody, I think, greeted this piece of work as something really novel, and it had some impact in other fields, and in particular, Stoddart and Jim Heath in California. So they tried to make an information storage device based on molecule, and they succeeded. So if you have a molecule of this type, but of course we will not discuss it from a chemistry viewpoint, if you can move a ring from here to here and vice versa, you are able to write, you are able to read by measuring the electronic conductivity of the thread here or the wire, and you can, at the end of that, you can erase and go back to the starting state. And so this allows you to write 0 or 1, read 0 or 1, and erase, go back to 0 for all the molecules involved. And I think it created a lot of excitement in the community, but also among physicists interested in memory system. So we have, many groups have been interested, let's say, after the years 2000 or 2005. And at the beginning of the year 2000, we started a project on trying to make artificial muscles. Muscles, just to remind you or to tell you how they work, muscles are not like springs. You do not contract matter, really. It's not like a metal spring. But you glide, you force gliding of filaments along one another. And so this is the natural striated muscle. You have a myosin, which is called the thick filament. You have actin, and actin is the thin filament. And when you contract your muscle, this is exactly what happens. The thin filaments will glide and move towards the center of this small fragment of muscle, which is called a sarcomere. And when you stop contracting, when you relax, the system will go back to its starting point. So you contract here, you consume energy, namely ATP. And when you relax, you know that it's not tiring. The system will go back. You will elongate again your muscle. You will relax your muscle. And so that was somewhat a big piece of work, actually, in terms of synthesis and measurements. And I will skip completely the synthesis and the measurements. But we made a molecule of this type. It's a slightly more complex rhotaxane than the one we have seen before. It is a dimer. You have two rhotaxanes, if you like, and they are connected in a very precise way. So an axis here, a ring here, and a dark blue axis here, and a dark blue ring here. And we could show that starting from the full length system, which is 8 nanometers long, we can contract, go down to 6 nanometers, go back to 8 nanometers using some chemical signal. We speak to the molecule using chemical reactions. And that was the first molecular muscle, so to say, of this type. Now let me show you the work of Ben Feringa, who is the third laureate, chemistry laureate in 2016. And what they have done is really fantastic. They were the first people to make a real rotary motor with a molecule. This is very, very technical, I know. I'm not going to talk about that. Simply, you can perhaps recognize here a double bond. See double bond. Like ethylene, you have 2 bonds between 2 carbon atoms. And if you have a double bond of this type, when you irradiate, when you shine light on it, UV light, the double bond will move, will rearrange, will be destabilized, and it will move. And this is what happens. Ben Feringa and his group published a beautiful video, and I will show you this video. So there are 4 steps. There are 2 thermal steps, so this is represented by this symbol, and 2 photochemical steps. And for the photochemical step, you will see a big flash of light. Very simple. So this is the starting form of the molecule. The double bond is here. And now this double bond will be destabilized and will be forced to move. So now we shine light, the system moves, we heat, it goes on. We shine light again, we heat, and we have done a complete round. And if you look at it carefully, I'm very confident that many of you will see that it rotates, it spins. Heating, the flash, heating again, the flash, and it rotates. And the beauty is that it rotates in one direction. Of course, otherwise it wouldn't be a rotation. It would be some kind of oscillation or pirouetting, but it rotates. And that was the first rotary motor made by chemists. Of course, they played many, many games. And in particular, there is something which is very popular nowadays, which is the field of nanocars. And nanocars, I think it speaks to all of us. You have a car, which is a molecule, and this molecule can move on the surface. Most of the time, it's a metal surface, copper or gold. It can also be graphite, I'm sorry. And so what they did, they made a molecule of this type, which looks like a car. I'm not sure it looks so much like a car, but yes, in to some extent. And they have equipped the molecule with 4 wheels, and here are the wheels. And now, if you shine light on these wheels, you will force them to rotate. And this is exactly what happened. It's a video which is, let's say, a bit science fiction. The molecule doesn't really roll like a car on a highway. It jumps, the motion is not really perfectly controlled. It jumps from one place to another. But they could show that this nanocar moves when it was not really shining light. It was injecting electrons to generate the excited state of the molecule. So now let me finish up by mentioning a few examples of molecular machines which have been made since the beginning of the field. The first papers were published in 1994. A pirouetting catenane, a molecular shuttle, we have seen that. A light-driven rotary motor, thanks to the work of Ben Feringa. In our group, we made molecular compressors which are able to encapsulate smaller molecules and compress them. Molecular pumps to store energy. Molecules which are able to walk exactly like kinesin, but they do not walk forever. They walk 2 or 3 steps, and then you have to start again the process. Compounds which mimic the ribosome by David Lee and his group. This is a fantastic piece of work, making small peptides with 3 amino acids perfectly, selectively, a little bit like the ribosome. Rotaxanes which can fly with flapping wings, and many, many other examples. And every day, now you have new systems of this type. So just to conclude, before the emergence of molecular machines, synthetic molecules were considered as still objects, as I already said, or objects undergoing random motion, and molecular systems undergoing large amplitude motions in a controlled way were basically unknown. The question you may ask is, so in which field is it going to be important from a practical viewpoint? These questions are very difficult questions, but there are already big projects oriented towards applications, and mostly artificial enzymes. Enzymes are kind of molecular machines. And if we can make molecular machines which behave as artificial enzymes, of course, it's going to be a big step towards applications in reactivity. Perhaps the most important potential application would be in medicine. If you can transport and deliver a drug exactly where the drug is needed, let's say close to a malignant cell, a cancer cell, or close to a bacterium or a virus, using molecular machines which can then deliver the drug, that would be a fantastic progress. And I would like to add that there is an additional motivation, at least for my group, which is that we have always been fascinated by biology, the complexity of biology, and trying to mimic in a very naive and primitive way what's going on in biology is certainly a big challenge. Again, I would like to insist that there are many possibilities. Okay, we will certainly, collectively, chemists will work towards those applications. But one should keep in mind that basic research is extremely important. It has been at the origin of basically all the technologies we are using today, be them in medicine or in new technologies. And so we have to trust the future that this field will probably be used someday for important applications. What I spoke about is a collective piece of work. It's a teamwork, and I would like to thank my team. We have no time, of course, to talk about all the people who contributed. I'd like to thank my university and the CNRS, the European Commission, my good friend Jean-Marie Lane, who is in San Sebastian today, who was my mentor, and a couple of other people, my family, and my two good friends, Fraser Stoddart and Ben Feringa. We were very, very happy to be awarded, the three of us, because we are close friends. We know each other for 40 years with Fraser and 30 years with Ben Feringa. And finally, thank you for your attention. Thank you.